Hello everyone, welcome back. Today we are starting onto a new math unit. We are talking about properties of circles. So you should know if you go from the very center to the outside, that is the radius. Cool thing about radius is if this is 10 centimeters right here, that means that this is also 10 centimeters, this is 10 centimeters, this is 10 centimeters. Anywhere you draw the radius, these lines are all exactly the same length. So that's a trick we're going to use quite a bit as we get into this. Next thing is diameter. Kind of like radius, except it's all the way across. And again, if you were to draw this diameter right here, or this diameter right here, anytime you draw a line all the way across, as long as it goes through the middle here, that will be exactly the same distance. Next thing, you learned about perimeter, and we have this Greek letter called pi. Pi is about 3.14. And so if you took pi and multiplied it by the diameter, you would get the perimeter, which is the distance all the way around this circle. Other formula is to say, let's still take pi, but instead of diameter, let's multiply by 2 times radius, which kind of makes sense, because this diameter is the same thing as this radius plus that radius again. So those are really the same formula, we just have them written 2 different ways. If you wanted to talk about area of the circle, you would take your same Greek letter pi, and you would multiply it by this radius squared. So it actually works out to be area equals pi multiplied by r, and then you're going to multiply by that same number again. So that should be review from grade 7 and 8. Let's talk about this line right here. This goes through my circle. It's called a secant line, but we're not actually worried about those right now. All of these lines are secants because they touch my circle in 2 different places. 2 different spots makes it a secant line, and we're not really all that interested in secant lines. What we are interested in is, what if I have a line that only touches in 1 spot right there? That is what we are going to call a tangent line. And we are going to be very interested in tangents. The reason why, there's a couple cool things about them. So that's our point of tangency. If you have a tangent line, so this right here is a tangent line, and if you draw the very middle of your circle, so that would be right there, if you draw the radius out to there, this angle is going to be 90 degrees every single time, which means this angle is also 90 degrees. And when we have a 90-degree angle, that should start triggering some September memories for you. Because now I have a right angle triangle right there. And same thing. Over here, I have another right angle triangle. And the reason why we like right angle triangles so much is because we spent like 2 weeks talking about the Pythagorean theorem. We are going to get to use that again, and we are going to get to solve some pretty cool things that you wouldn't think you could do with things just based on having a tangent line and a radius. So let's start with a question like this. We'll start out a little slower. I told you that this is a tangent line right here. This is the radius because it goes down to the center, which means that angle has to be 90 degrees. The other thing I know is that all of the angles if you have a triangle, all of the angles have to add up to 180 degrees. So what I can do is I can say I have 90 degrees right here, I have 63 degrees right here. Whatever x is, that has to be the amount to make it all add up to 180. So what I'm going to do is say 180 degrees minus 90 degrees minus 63 degrees. That will equal my x over there. So when we do this, 180 minus 90 is 90. And then 90 minus 63 is 27. So we can say that this angle right here is 27 degrees. Next thing we can do, kind of the same idea here. We have a tangent in this line, and we have the radius right there. That means that's 90 degrees. So I can go 180 degrees minus 90 minus 41, and I get an answer of 49 degrees right there. So let's now go back to our Pythagorean theorem. And I'll review just really quickly here a couple things you should remember. First thing is you should remember that formula. And the other thing you need to remember is what do each one of these letters here correspond to on the actual triangle. And I'm going to highlight C in blue there. When we have our right angle triangle, the way that we label this is that A and B, those are the two legs. And when I say legs, I mean find your right angle, and then the line coming off, that is one leg. This line coming off, that is another leg. And so it doesn't actually matter which one we call A and which one we call B, but for the purposes of this question, let's say that's A, that's B. If you did them the other way, you would have no problems. It'll be exactly the same. C is always the longest side, and it's always across from the right angle. So your C will never actually be touching that right angle there. It'll always be across the triangle from it. Okay, that's Pythagorean theorem. Now that we have two of these numbers, we can plug those in to this equation. And from there, we can solve for the one that we don't have. So let's do that. A squared plus, when I'm substituting, I'm going to use brackets. 14 meters squared equals 17 meters squared. To make this a little easier for myself, I'm going to figure out what each of those things actually are. So we will go on the calculator. 14 times 14 is 196. And I'm also squaring my units, not just the number. So it'll be meters squared. And then 17 times 17 is 289. Same thing. Square the number, square the units. Now I've got an algebraic equation that I can solve here. So I can say, okay, I am adding 196 meters squared. The opposite of that would be subtracting 196 meters squared. I'm going to do that on both sides. So I keep my equation equal, and it'll cancel out on this side. If you go 289 minus 196, you get 93. And then the last thing, I have a squared right here. I don't want to have a squared. I want to just have a. So the way that I get rid of that exponent is I do the square root. But to keep it the same on both sides, do the square root on both sides. And you should get 9.64. We'll say 2 decimals here. But I also have units. So when I did, like back up here, I said that this squared has to go on to the number as well as the unit. Onto the number as well as the unit. Same thing happens with this square root. So I square rooted the number. I also have to square root the unit. If you take the square root of something squared, you get just that thing. That's how we got from a squared down to just a. So we'll end up with just meters there. .64 meters. I'm going to just double check, make sure that number actually sounds reasonable, because sometimes you get numbers that are way off if maybe you forgot to do this square root, or if you forgot to square one of these. So 9.64, that is smaller than 14 and 17, but it's not so much smaller that it doesn't even make sense with the diagram. So I'm pretty happy with that answer.